Let's look now at integral calculus involving inverse trig functions. So what we want to do is start with the idea of our general standard forms of the integration of trig functions. So what are the forms? And remember, this is just a reversal of the derivative of the functions, so anti-differentiation here. So we've got 1 over the square root of 1 minus x squared. That comes back to inverse sine of x, like we saw in our last videos. Or you could also have it coming to minus cos of x. So if you derive either of these, it will get to 1 over the square root of 1 minus x squared. So it doesn't really matter which one you take it to. Both are correct. So if you have this situation anytime, go to either positive inverse sine or negative inverse cosine. 1 over 1 plus x squared, well, that will integrate back to inverse tan of x. Try not to forget your constant integration, especially if there's an application of it there. This time with 1 over the square root of a squared minus x squared. Now notice this carefully, okay? It's 1x squared. The a squared minus x. So it's some number minus the x squared. X squared is monic there. So you've got to be careful with that. So, and we'll see that in some of the problems we'll face. So that comes to x on a for the inverse sine, or minus inverse cos of x on a. So be wary of that. For the tan, again, it's monic here, but it's a squared plus x squared. So we can do that. Now, if you're looking, going, well, what about a squared minus x squared? Well, that's a different situation. If it's minus, you can actually break that up. We won't have that in this course, but you could break that up into two different factors and solve it. They would actually come to log functions. But you need to use a technique called partial fractions to solve that one, which is extension 2. So the extension 2 kiddies will do that, but for extension 1 we don't treat an integral of 1 over a squared minus x squared. A squared plus x squared doesn't break down, and it goes back to being an inverse tan function. So keep those in mind. They will be in the back of your exams as the as table of standard integrals. So you'll be able to see those there and play with them at that point. So let's have a look at some problems. This is in the form already where it's in an a squared minus x squared. So we could leave it in two ways. We either put it as inverse sine of x on 3, because we take the x there and the 3, or minus inverse cos of x on 3 with our constant. Either way, that's fine. This one, definite integrals, because again, as we should have said before, all the applications we've had of integration in the 2-unit course and the extension 1 course so far, it's going to hold here. So we can find definite integrals. So 3 over 1 plus t squared. Well, the 3's really got nothing to do with it, so that can come out the front. And because the 1 over 1 plus t squared integrates to inverse tan of t, we're going between 0 and 1. So we substitute 1 in, substitute 0. Remember, we're working in radians. And so inverse tan of 1 is pi on 4. And inverse tan of 0 is 0. So we get 3 pi on 4. So there's how that one works. Again, another one with a definite integral. Again, this one's in a pretty standard form. The 2 can come out the front. It makes no difference. 1 over the square root of 1 minus x squared integrates to sine of x. Again, you could have put minus cos. So it could be minus 2 inverse cos of x. Substitute your values in. You will get back to these values and you'll be able to solve it. Exactly. It should come out the same answer. If you're not too sure, have a go. Put minus 2 inverse cos of x in. Substitute 0 and root 3 on 2 in, and see if you get back to 2 pi on 3. This one takes a little bit more manipulation. Now notice we've got the 1 over square root of 1 minus 4x squared. Now that's a little bit different. Remember, when we integrate, we want that form. A number squared minus x squared. So it's got a number in front. So what I want to do is factorize that out. So it takes a little bit of manipulation. So if you see, you've got I factorised it here. So you've got a 4 outside of a quarter minus x squared, because I factorised it all out of all of it. Now, the square root of 4 could be written as 2. So I can write that as 2 square root of a quarter minus x squared. And then I can take that out as a half. So that one's more easily manipulated because we can do that integration straight away. So this would become a quarter of minus x squared. So square root of a quarter is a half. So that's why we get the half in the denominator there. And obviously the x. So it's x on the a, and where that was a squared. So that would give us a half inverse sine of 2x plus the constant. So that's how that one works. We need to do a manipulation. We can't do it until we've just got a 1x squared there, because we can use that form then. And that's what we want to aim for. Aim to get that form to be able to integrate it. Question 5 here, same thing. Notice we've got a 4t squared. We want a 1t squared. It's a little bit easier with this function because there's no square root to make it more difficult. But if we factorize 4 out and put the quarter out there, we get 5 on 4 plus the t squared, which means we take the quarter, because that's just out the front. That's making no difference, the constant. 1 on a, which would be the square root of 5 on 4, or square root of 5 on 2. And t over the square root of 5 on 4. The square root hasn't been put in there, but it should be the square root of 5 on 4 there. Which again, that can come down to the square root of 5 on 2, which we can change around and take the reciprocal of that. So that's where we get 2t on root 5. And that could be written as 2 on root 5 there, and the 2 would cancel with the 4. That's where we get the 1 on 2 root 5 there out the front. So again, make sure of that manipulation, that you're able to get back to just the 1t squared to integrate. Curve sketching, and then using that to find the area. So sketching the curve 1 over x squared plus 1. Well, what does x squared plus 1 look like? It looks like that. So when we put 1 over it, notice all the values, the smallest value is going to be 1. They're all positive, so the highest value of 1 over x squared plus 1 will just be 1. And then all the values are getting smaller. So again, why do we do a sketch of a curve? Because we want to see if our area is going to go below the x-axis. It doesn't. We're just dealing with this area here, between 1 and root 3. So there's no complications in having to go above and below the x-axis, so we don't have to put anything in absolute values here. So again, we'll integrate between 1 and root 3 of 1 over x squared plus 1, or if you like, 1 plus x squared. That integrates to an inverse tan function. We sub our values in, and we'll get pi on 12. Another area situation here. The graph's already done for us, so that's not too bad. We're going between minus 3 and 3, so again, it's symmetrical here, because that's symmetrical. And so we can just go 2 lots of 0 to 3. 1 over the square root of 25 minus x squared, integrates back to inverse sine of x on 5. We sub our values in. 3 significant figures, because it's 0 to 3, so it's not going to give us very nice values. But when we put that all into the calculator, to 3 significant figures, we get the 1.29. We can also do volumes questions. That's part of integration as well. So we get the 1 over square root of 4 plus x squared between 0 and 2. Remember, because we're rotating it, we're getting circular discs. We're going to get our pi y squared dy dis. So we're going to go from 0 to 2. That was given to us. And the 1 over the square root of 4 plus x squared, well, square root goes nicely. So 1 over 4 plus x squared integrates to a half inverse tan of x on 2. And we're going between 0 and 2. So we can factorise the half out and just have pi on 2 out the front. Sub our 0 and 2 in. And we're able to get down to pi squared on 8. Don't forget our units cubed. And we can also see this one with inverse tan functions there. Correct as 3 significant figures. You can do a table and try and get your values there. Or you can just start to say, look, because it's between 1 and 3, you're going to go, the h is going to be a half. It's going up by a half each time. So our first value is 1, our last value is 3. Our odd values are going to be inverse tan of 1.5 and 2.5. 4 lots of those, and the middle value there, so the only even value is 2, so inverse tan of 2, and we're doubling that. You can throw that all straight into the calculator, and then calculate the 3 significant figures. You can do your table, but it's just going to be easier putting the exact values straight into the calculator to start off with, rather than calculating and then do a decimal approximation. Make sure you get your h right, and it's over 3 because it's Simpson's rule. So we just put in the values in and applying the rule. So there you go. There's inverse functions with integration. All the same applications we've done before, except now with a couple of extra rules to learn with our integration of the trig expressions, inverse trig expressions.